Good afternoon, students. In this lecture, we will continue our previous lecture on AC power analysis. We will see effective or RMS value, apparent power, real power, reactive power, power factor, and these are very important concepts in electricity or in the study of electric circuits. Okay, let's start with effective or RMS value. What is the effective or RMS value? The total power, if I have, for example, here AC source, and I have a current, this is the resistor, the load, then the total power dissipated by the resistor is 1 over T, which is the fundamental period, the integration from 0 to T, I square times R times dt, because R is constant. So I is the alternating current. So we have to integrate with respect to the current. So I squared dt. So it means R over T integration from 0 to T I squared dt. And we can write it in short, IRMS squared times R. From what is IRMS? From this relation, if we remove R, IRMS, or we call it also I effective, or the effective current, is the square root of 1 over T from 0 to T I square of T dt. So we square the current, we integrate from 0 to T, and then we divide by capital T to get the average, and then we make square root. So it is also called root mean square. So root means square root, mean means the average. The average, how we get it? Because we divide it by a period, 1 over T, and the mean of the square means the integration of this divided by capital T. So IRMS is defined by this equation. So the power delivered to the load, to the resistor, is simply IRMS square times R. The RMS value is a constant value, okay? Depending on the type of current we have, the AC current, we will get a value which is constant here. So what is the meaning of this constant value? Actually, this IRMS means the equivalent current. If I have, for example, a DC source, it is the equivalent current if I have a DC source, and that DC source giving the same amount of power like the AC source here. So it's like if I have a DC current, for example here, it will be IDC square times R. So that means that IDC is equal to IRMS. So for any variable or for any periodic function, it can be voltage or current. The RMS value is defined by, if I have x of t, this is current or voltage, the square root of 1 over t integration from 0 to t x square t dt. The effective value of a periodic signal is the root mean square value. That's why it is called RMS. The square root of the mean of the square value. The mean of the square is from 0 to t x square dt divided by t. So let's say I have a current I of t, Im cos omega t. This is the AC current. Let's find the RMS value. IRMS is equal to square root of 1 over t from 0 to t Im square cos square t dt. And if we use the trigonometric identity for cos square theta is equal to 1 plus cos 2 theta divided by 2. So this will be 1 plus cos 2 omega t divided by 2. Then Im square is constant. We can take out of the integration, and we have the integration of this. The integration of the first part will be t, and then it will be t over 2. The second part, because it's cosine, you can try it. The second part, the integration of the second part is 0. So from this I will get T over 2 times T. T will cancel T. And finally I have Im over radical 2. This is the RMS value. So we can just quickly get the RMS value from the function itself. So if I have Im cos omega t, what's the RMS value? Im divided by radical. If it is a voltage, for example, Vm cos omega t, what is the RMS value? Vm over radical 2. Now, if in the previous lecture, when we talk about the power, what did we say? Power is 1 over 2 Vm, the peak value of the voltage, Im, the peak value of the current, cosine of theta V minus theta I. So theta V minus theta I is the angle difference between the voltage and the current, as you know. So we have this, but Vm, we can write this as Vm over radical 2, Im over radical 2, which is Vrms times Irms cosine of theta V minus theta I. This is another way to write the power. So the RMS value of any sinusoidal current is Im over radical 2, and the average power can be written in terms of the RMS. It will be Vrms times Irms cos theta V minus theta I. Okay, if in case we express the phasor voltage and the phasor current in terms of RMS value, we just take the RMS value directly. But if we express the phasor voltage and the phasor current in terms of the peak voltage and the peak current, then we have to make Vm over radical 2 and Im over radical 2, which is Vrms times Irms. Apparent power is the product of the RMS value of the voltage and the current. The unit of the apparent power is volt ampere, because I have voltage times current. To distinguish it from real power, which is the unit of power, the real power is watts. So P now, okay, the real power is Vrms times Irms cos theta V minus theta I. Vrms times Irms is called the apparent power. What is the unit? Volt times ampere. Okay, the unit of voltage and unit of current is volt times ampere, and we find it as the unit symbol VA, volt ampere. So the real power is S cos theta V minus theta I. The cosine part is called the power factor. This is called the power factor. So what is the power factor? The power factor is P over S, which is equal to cos theta V minus theta I. So if I know the real power and the apparent power, the real power divided by the apparent power will give me the power factor. The power factor is the cosine of the phase difference between the voltage and the current, or it is the cosine of the angle of the load impedance. Why? Because if I have, for example, the impedance, if I want to calculate the impedance Z is V over I. And in phasor form, Vm at an angle of theta V over Im at an angle of theta I, which is Vm over Im theta V minus theta I. When theta I goes up, it will be minus. So if I express as the impedance in phasor form, we have Vm over Im at an angle of theta V minus theta I. So this angle, in fact, the cosine of this angle, it gives me the power factor. So I can get it also from the impedance. That means the power factor can be known from the impedance. The same if I use RMS value here. So if theta V is minus theta I is positive, we call it a lagging power factor, remember. So Lagging power factor means the current lags the voltage. The current lags the voltage means theta V minus theta I is positive. And in this type of load, we have mostly inductive load for this case. If I have lagging power factor, inductive load. If theta V minus theta I is negative, we have leading power factor, and we call current leads the voltage, and the load is capacitive load, because for the capacitive load, the current leads the voltage. Okay. For a purely resistive load, the voltage and the current are in phase. That means theta V minus theta I is equal to 0, which means the power factor is 1. For a purely reactive load, theta V minus theta I, for example, if it's inductive load, is 90 degree, the power factor is 0. If it is capacitive, minus 90, the power factor is 0. The power factor is an important parameter because it affects the electric bills consumers pay to the electric utility companies. It determines the amount of real power consumed by the electrical loads we have in our homes. For example, washing machines, refrigerators, air conditionings, all this. So the power factor is very important, an important element which affects the electric bill in our homes. Okay, so let's have here an example. A series connected load to the voltage draws a current of I of t for cosine of this, and the voltage is given by this. Find the apparent power, the power factor of the load. Determine the type of electrical element that forms the load. Okay, very easy because the voltage is given, the current is given. What is the apparent power? Vrms times Irms. Vrms is V peak over radical 2. Irms, I peak divided by radical 2, 240 volt ampere. Unit is volt ampere. Power factor. What is the power factor? We take the angle of the voltage, both are in cosine here. So the angle of the voltage is minus 20, the angle of the current is 10, minus 20 minus 10, minus 30, cosine of minus 30, 0.866. What type of power factor? Leading or lagging? Leading, because the current leads the voltage. The power factor is leading because the current leads the voltage. The power factor may be obtained also from the impedance. Let's calculate the impedance. Z equals to V over I. V is 120 at an angle of minus 20. For I is 4 at an angle of 10. Then we have 30 at an angle of minus 30. And this is polar form. When we change it to rectangular form, we have this one plus minus this one. This is the real part and the imaginary part. As you see, it is minus J. Minus J means it's capacitive. Why? Because the impedance of a capacitor, remember, ZC is 1 over J omega C. So when J go up, it will be minus J omega C, minus J over omega C. So if, for example, we can find exactly the capacitor value. So XC minus JXC, remember, XC is negative 1 over omega C. This is equal to minus 15. Minus 15, the imaginary part here. So what is omega? 2 pi f. 2 pi f. So it is omega is here already. It's given 100 pi. Omega is given 100 pi, and XC is 15. So substitute 15. So 1 over 15 times 100 pi will give me 212.2 microfarad. Okay, this way we can know exactly the capacitance value. Okay, now if I have, let's summarize here, if I have a purely resistive load, theta V minus theta I, the angle between the voltage and the current is 0, meaning the power factor is 1. So all power is consumed. If I have a purely reactive load, which is inductive load L, or capacitive load with C, theta B minus theta I is 90 degree, positive 90 degree for inductive load. So the power factor is 0. That means no real power is consumed. For the capacitive load also the same. If I have a resistive and reactive load, so both the resistance and, for example, inductance or capacitance, theta V minus theta I greater than 0 for inductive load. That means there is a resistor and inductor lagging load. The current lags the voltage, and theta V minus theta I less than 0. And in this case, we call it leading load or capacitive load. Okay, complex power. And complex power is the product of the voltage and the complex conjugate of the current. So if I have here a load here, the voltage V, Vm at an angle of theta V, the current I, phasor form, Im at an angle of theta I, the complex power is S 1 over 2 V times I conjugate. Okay, or another form, Vrms times Irms at an angle of theta V minus theta I. This is the complex power. Why minus? Because I conjugate, right? This is a complex power. If you remember, the real part of this complex power will give me the real consumed power. So here is again the formula 1 over 2 VI conjugate VRMS IRMS is, and if I expand it, it will be VRMS IRMS cosine of theta V minus theta I, J IRMS VRMS sine of this. This part we call it, like for example Q, the symbol for it is Q, the reactive power, and the unit is volt ampere reactive. Okay, to identify it from volt ampere, we call this, the unit of Q is volt ampere reactive, and this one is the power P, the real power P, and the unit is watt, and the unit of S is volt ampere. So P is average power in watts delivered to the load, and it's the only useful power. Q is the reactive power exchange between the source and the reactive part of the load. It is measured in volt ampere reactive. Q is equal to 0 for a resistive type of loads, which means the power factor is unity in this case. Q is less than 0 for a capacitive type of loads, and we have leading power factor, and Q greater than 0 for inductive type of loads, lagging power factor. Okay, same now, same, this is a repetition. Okay, if we write it again, the complex power S, P, J, Q, VRMS, IRMS conjugate, VRMS magnitude, IRMS magnitude, at an angle of theta V minus theta I. So the apparent power is magnitude of VRMS times magnitude of IRMS, which is the square root of P square plus Q square, and the real power P is the real of S, which is the apparent power times cosine of theta V minus theta I. The reactive power is the imaginary part of S, which is the apparent power times sine of theta V minus theta I, and the power factor is P over S, cos theta V minus theta I. Now, this is a vector representation, how we represent it in vector form. For example, the x-axis is the real power, so we draw it in the x-axis, P, and the y-axis reactive power, Q. So we have a right angle triangle here, and the hypotenuse. The hypotenuse is apparent power S. And remember, S cosine of theta will give me P, the real power. right? So theta is tan inverse of Q over P. And here the impedance also in terms of the power factor here, R the resistor on the x-axis, X the reactance in the y-axis, and the hypotenuse gives me the impedance, the magnitude of the impedance Z. So if I have here, for example, P here, and for inductive type of load, I have Q positive, Q lagging power factor. So P, the vector P plus the vector Q, they form right angle here, and the resultant vector is S. S is the resultant vector, which is the complex power S. Okay, and S cosine of theta V minus theta is P. S sine of theta V minus theta I is Q. Or remember, this cosine of theta V minus theta is the power factor. And for the leading power factor, the same, but Q is negative here, and P, the resultant vector, will be this one. Conservation of AC power. Okay, if I have a source here, a complex power, if I have a source here, I have a complex power. The total complex power is equal to the sum of all powers of the sum of all powers of the individual loads. Okay, so if I have, for example, two loads here, Z1 and Z2, the total complex power S is equal to S1 plus S2. Also for series connected loads, also the same. So the complex power supplied by the source, assuming all values of voltage and currents to be RMS, for example, is S V times I conjugate, V times I1 conjugate plus I2 conjugate, VI1 conjugate, VI2 conjugate, S1 plus S2 for the parallel load, this one. Okay, now power factor correction. We need power factor correction to reduce the total current coming to our load. Because if we reduce the load current, then we reduce the amount of energy consumed, and we are paying less bill. Okay, for the electric, for example, if we are paying for FIWA or DIWA, electric power authorities, then reducing of our electricity consumption means energy is reduced and we will pay less cost. So power factor correction is very important. So what is power factor correction? It is the process of increasing the power factor without altering the voltage or current to the original load. So that means, for example, if I have a load here, this is inductive load. This can be, for example, our AC, the air conditioning. We model it, for example, by an inductive load, or it can be refrigerator or some other load. So we have here inductive load here. Then I have the load current IL, and we have the voltage across it. So without changing this voltage, we apply a parallel load capacitor, okay, a capacitive load here to correct the power factor. That means to increase the power factor. Increasing the power factor means increasing the value of cosine of theta V minus theta I. Remember, okay, the angle between V and I, cosine of theta V minus theta I. The cosine of that. So the cosine of that, we increase the cosine of that means we increase the real power consumed by the load. So by applying a capacitive load here without changing the voltage across the load, we can minimize the current I. So minimize the current I means from economical point of view, we are reducing the energy consumption of our usage from the electrical loads so we are paying less money. Okay, that means. So it's very important. So here there are some notes you can read. Power factor correction may be required where a system has a power factor of less than 90%. If the system has a power factor less than 90%, that means if the cosine of theta v minus theta I is less than 0.9, so we usually need a power factor correction. A poor power factor can contribute to equipment instability and failure, as well as significantly higher than the necessary energy cost. Okay, by optimizing and improving the power factor, power quality can be improved, reducing the load on the electricity distribution system. Okay, now let's try to look here what it means from power factor correction. I maximize this. Okay, let's see. This is my load, inductive load first, and I have this capacitor. So originally I have an apparent power of S1. This is my apparent power S1. Okay, this is the original apparent power, which is V times I, for example, in this case, V times IL. So after that, the real power is this one. So we don't change the real power. But now the apparent power change from S1 to S2. How does the apparent power change from S1 to S2? By having a reactive power QC. By applying a capacitor, we have a negative reactive power. So originally, Q1 was from this point until this point. Okay, from this point until this point is Q1. Q1 is this. So when we apply QC, because it's negative, Q1 minus QC, Q2 will be smaller. So Q2 will be smaller than Q1. Why? Because QC is negative, because it's a capacitor. So Q1 minus QC will give me Q2. Okay? So or in other words, Q2 is Q1 minus QC, or QC is Q1 minus Q2. But what about P? P doesn't change. The real power doesn't change. So now the resultant vector S2 is becoming smaller than S1, as you see, which means the current will reduce and our electricity consumption will reduce. That means, okay, the electric current. So this is from the power triangle point of view. Now Q1 is what is Q1? S1 sine theta 1, or in terms of P, P times tan theta 1. What is Q2? P times tan theta 2, because the angle changed from theta 1 to theta 2. The power factor is corrected. Which one is bigger? Is cos theta 1 bigger, or cos theta 2 bigger than cos theta 1, or cos theta 1 bigger than cos theta 2? It's clear that cos theta 2 is bigger than cos theta 1, because cosine, remember, the angle is smaller. So cos theta 2 is bigger than cos theta 1, means our power factor is improved. Okay? And P is staying the same. Now Q2 is P times tan theta 2. Q1 P times tan theta 1. So QC will become Q1 minus Q2, P times tan theta 1 minus tan theta 2. But QC in terms of the voltage, because the voltage does not change for the parallel loads, V square divided by the impedance of the capacitor, so the ZC. So V square divided by 1 over omega C. Then 1 over omega C, when it goes up, it will be omega C times V square, VRMS square. So this is QC. Remember, this is an additional part, QC. So which will correct our power factor from theta 1 to theta 2. So C can be easily calculated from this relation. What is C? C is QC over omega V RMS square, but QC is P tan theta 1 minus tan theta 2 over omega V RMS square. So by this way, we can calculate the value of the capacitance used to correct the power factor from theta 1 to theta 2. This is the current and the voltage diagram. Okay, let's say that this is the voltage, and of course the current leads the voltage if I in the capacitive load. IC leads V, so by 90 degree. So you see perpendicular, IC is perpendicular to V, and IL here is lagging. Originally I was having theta 1. This is the original load, the power factor of the original load, theta L. Why? Because V leads IL. The voltage leads the load current IL here. So I have theta 1. Then theta 2 smaller than theta 1. Now I apply this IC, the current IC. Okay, IC is this. So the addition of IL plus IC will give me the resultant vector I, which is after power factor correction. You see? So if we see I, it becomes smaller than IL, which means the current reduced. So the energy consumption reduced and the power factor is corrected. That means. Okay, now let's see example. Example, when a 120 volt connector to a load which is 4 kilowatt and the voltage 60 hertz and the power factor is lagging 0.8, find the value of the capacitance necessary to raise the power factor to 0.95. So the original power factor is 0.8 and we want to improve it and make it 0.95. So we should find the required capacitance. So we have to use this formula, that means. So we need to calculate P tan theta 1 and P tan theta 2. That means tan theta 1, tan theta 2, and voltage is given, and we just use the formula. Okay, power factor, the original 0.8 means cos theta 1 0.8, theta 1 36.87 degree. Okay, the inverse of this, cos inverse of 0.8, and the original apparent power S1 cos theta 1 is P, so S1 is P over cos theta 1. The original apparent power is 5000 volt ampere. Q1, the original Q1, S1 sin theta 1, sine of this, 3000 volt ampere. Cos theta 2, now the after power factor correction 0.95. So theta 2 18.9 degree, okay, smaller than theta 1, remember. Okay, now the real power has not changed, okay, but the apparent power has changed. It's what's the new value of the apparent power? S2 is P over cos theta 2. Okay, so 4000 over 0.95 is equal to 4210.5 volt ampere. Okay, you see S2 is smaller than S1. S1 is 5000. Okay, so Q2, what is Q2? S2 times sine theta 2. So this S2 times sine theta 2 will give me this. Now QC is Q1 minus Q2. The difference between the two will be QC, 3000 minus this one, 1685.6 volt ampere reactive. Therefore, the required capacitance C is QC over omega V RMS square. So this is QC 2 pi, and the frequency is 60, and the RMS voltage is 120 square. We get 310.5 microfarad. So this is the required capacitance to improve the power factor from the original value 0.8 to 0.95. Note that for 120 volt 120 volt RMS, we have a peak voltage of 170. So the capacitance, when we purchase, they are rated with respect to the peak voltage. So we would suggest purchasing a capacitor with a voltage equal to, for example, 200 volt, higher than this rating for the safety of the capacitor itself. So the rating should be 200 volt or higher than 130 volt. Okay, this is a practice problem. So it's similar. Find the value of a parallel capacitance required to correct a load of 140 kilovolt ampere reactive. Note that here what is given, Q1. Q1 is given. Q1 is kilovolt, because why? Because the unit is volt ampere reactive. So kilovolt ampere reactive. And Q1 is given, and the power factor is given, 0.85 lagging. And we want to change from 0.585 lagging to unity power factor. So that means theta will become 0. Unity power factor means theta 2 will become 0. So cosine of 0 is 1. So we need to find the required capacitance, which is used to correct the power factor from 0.85 to unity power factor, or 1. And based on the previous concepts, you can be able to solve this. The answer is given. It's a practice problem. So please redo the examples and the practice problems in this chapter. And with this, we finish the topic about AC power analysis. Thank you for listening to this lecture.